All right, so I was saying that for this one, we have something like this: cosine of 1 radian divided by 1 to the fourth plus cosine of 2 radians divided by 2 to the fourth plus cosine of 3 radians divided by 3 to the fourth, and so on and so forth. This one is sort of strange as well because you don't know what's happening here. Some of these might be positive, some of them might be negative, and the pattern might be all over the place. So what we do is we consider the absolute value here, the absolute value of cosine of n all over n to the fourth. And what can we do with that one? Well, we know that guy is less than or equal to 1 over n to the fourth. Why? Because the cosine of an integer is always, in absolute value, is always smaller than 1. And when I know that n is also greater than or equal to 0 all over n to the fourth. And so by using the direct comparison test, I know that this one converges, for example, by integral test. Then by direct comparison, then this one converges. Then by the absolute convergence test, this one converges. And so there you go. We had to use several tests for this one, but we got the job done. Using the direct we'd consider the absolute value. Then using direct comparison, we said it's smaller than that, and of course positive. Then using the integral test, we know this one converges. This one is smaller and positive. That forces this one to converge using direct comparison. And then by the absolute convergence test, that forces the original one to converge. So this one converges. And then we're done. Beautiful. Okay. How about this one? This one, all right, so let's say you have this one which has annoying integrals, alternating signs. You got -1 all over 1 plus 2 over 2, plus 1 over 2 plus -1 over 3 plus 1 over 4 plus -1 over 5, blah, 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 blah. Suppose you think to yourself, you know what, that's a bit annoying. Let me try the absolute value version of that, -1 over n. If we try the absolute value version of that, that gives us just 1 over n, which diverges. Then what can you say according to the absolute value convergence test? Well, nothing, because the condition is only met if the absolute value version of the series converges. This thing says nothing, absolutely nothing, if that one diverges. So this test is inconclusive. The absolute convergence test is inconclusive. So what else do we have to do? We have to try some other test. And so we skip the alternating series test. Alternating convergence test. So we try the alternating series test. By alternating series test, you have this switching of the signs. And you have 1 over n is decreasing monotone and going to 0. Therefore, summation of -1 to the n over n converges not by the absolute convergence test. It converges by some other test we have to work on, by alternating series test. So in this case, we were able to show that the series converges, but not using the absolute convergence test. That one failed. Now when that happens, as I said earlier, this is called a conditionally convergent, as opposed to absolutely convergent. Because, as I said before, if one of them diverges and the other one converges, it's called conditionally convergent. Okay? That's how we handle those. This is the same one. This one would be also conditionally convergent. If I tried to do this version, -1 over n all over square root of n, this is equal to summation of 1 over square root of n. That's bigger than summation of 1 over n. that's going to diverge. So there, this one converges by alternating series test. Therefore, the series is conditionally convergent. Okay, one of them diverges. The absolute value version diverges, but the original one converges using some other test. Therefore, it's called conditionally convergent. Okay. Same for this one. Conditionally, no, this one is, let's see what this one is. Clearly converges by alternating series test. But let's see if its absolute value also converges. So let's consider -1 to the n all over n to the 5 square root of n. This is equal to the square root of 1 n to the 5.5. By using the integral test, this converges by the integral test. I know that because this is such an easy one. Therefore, the series is absolutely convergent. Because I'm applying, if that one converges, then the original converges, so therefore both of them converge. Therefore, it's absolutely convergent. Okay? That's very different than the previous one we did. This one, if you slap some absolute value here, so you ruined it, diverges. But if you leave it as the original one and use some other test, it converges. Then this one converges, but its absolute value version it doesn't, so it's called conditionally convergent. Okay? And that's about it. That'll do it for us today. All right. We'll see you guys next time. Thanks. Bye.